So now let's dive into gases. This is fun. This combines so many exciting things. And also, so the next set of chapters we're covering for Exam 4 will be 5, 11, and 12. This section of notes also covers Chapter 19, which is not on Exam 4, but is on the final, so it's included in this section of your notes packet. You guys, we're almost done with your packet. Look how far we've gone. It's amazing. And we'll get this joke later, but anyway, so 5, 11, 12, they don't lead into each other as well as 7, 8, 9, 10, but you'll see how some of them do in fact go together. But what we want to talk about right now is Chapter 5 with gases. So the experiment you're doing this week is to discover the gas laws / confirm them, because I'm going to tell you them in a minute. But what we're focused on is thinking about all the different factors that affect gases, the units. So we're diving back into kind of Chapter 4-y type material, because we're going to be working a lot with units. Sig figs are going to be a thing again, so remember that stuff. We're going to be using our calculators heavily again, so make sure you're bringing it with you. So we'll talk about different ways we can calculate quantities, things like density and molar mass that we can figure out, and just how we think about the movement of gases. All right, so the first thing we're going to talk about is the gas state and all the units that are important when we're talking about the gas state. So the gas state is the least condensed state of matter, which means the atoms are pretty far apart. So what we know from this is that gases are much less dense than liquids or solids. So we briefly brushed on this when we started talking about chemistry in general. We talked about the states of matter, and we said that when we're talking about gases, the unit is not grams per milliliter or grams per centimeter cubed like we had with other states of matter, but grams per liter, because they're so much less dense. So the density has units of grams per liter because there's not a lot that occupies a certain amount of space. The other thing about gases is that the volume that they take up is greatly affected by pressure and temperature. So unlike other states of matter where the molecules are really close together, in a gas they're all really far apart, so the pressure and the temperature are really important. Another thing that's important about gases is that you can mix them easily with each other. So we say they are miscible. Miscible is a fancy word for mixable. I don't know why they didn't just call it that, but you can think of it that way. So they can be mixed with each other in any proportion. And I should say with the small caveat that that's not true if they react. So unless they react with each other. But most of the time, gases are not super reactive, just sitting around, so you can mix them easily. So I would say that the most important thing here is that the atoms or molecules are relatively far apart. So if they're not very close together, that means that they don't interact with each other very much. So we say they have negligible or very small intermolecular interactions. So that's just a fancy word for saying, fancy bunch of words for saying they don't really interact with each other. Or we can assume for the most part that they don't interact with each other because they're far enough apart. And we say that in general, if something is a gas, it's going to have similar properties to other gases because of how they react. And it's really more or less independent of their chemical identity. So gases have similar properties independent of their chemical identity. So we don't say the same, but relatively similar. How much space they take up, the pressure, etc., just because they are gases. Okay, so the unit thing is super important for gases, and we have 4 units or variables that we're going to be interested in. So one of them is moles, which we use the variable N. This tells us how much of the gas we have. Grams is going to always be a really small value, so moles is an easier quantity to use to be able to correlate different qualities about the gas. Okay, also volume. And the volume that we're going to be measuring is going to have units of liters. Sometimes you're told stuff in milliliters. You want to use liters because that's going to give you a direct relationship with other variables. The other thing we're interested in is, any guesses? Temperature, exactly right. So I just said that the volume is affected by pressure and temperature, so temperature is definitely one of those things. Has the variable T, and usually the temperature has units of Kelvin. Remember that whole thing? So to get units of Kelvin, you just take the temperature in degrees Celsius and add 273.15. Why do you have to do that? Because, again, otherwise your relationships between the different variables won't work out linearly. So the last thing is pressure, P, and it has many different units. Okay? So that's why the whole next page is dedicated to talking about pressure and all of its different units. See how it just flows together so seamlessly? Okay, so let's talk a bit about gas pressure, because what we've already said is that the molecules are far apart, they don't really interact with each other, so it's not super helpful to try to weigh a gas out. It's more helpful to think about what is the pressure of the gas in the container. And where does pressure come from? Pressure comes from the gas molecules hitting the walls on the container and exerting a force. So from physics, we know that pressure is the force over the area, and that pressure would depend on how much of the gas you have. Okay, so when we're talking about pressure, a lot of the time we have to think about atmospheric pressure, because living on Earth, we have an atmosphere, which means we have a bunch of gases surrounding us at all times. We need to know what the pressure is from all of those gases. Okay? So it's the atmospheric pressure is the force exerted by our atmosphere onto Earth's surface. So we have to care about this because we live on Earth's surface. So there you go. Okay, so the atmosphere is composed of a bunch of gases. What gases are they? Nitrogen, yep, so it's 78% nitrogen. What else? How do you survive? Oxygen, yep. About 21% oxygen. What else? Carbon dioxide, yeah. You're doing an assignment on that, so hopefully you know that carbon dioxide is a thing. Currently 0.04% CO2 and rising. Anything else? Weirdly, argon. So 0.9% argon, and others. But the most prevalent ones are nitrogen and oxygen. The actual pressure of the atmosphere that gets exerted on a single day depends on your altitude, so how far you are from sea level, and the weather on a given day. Okay? So the standard atmospheric pressure at sea level is defined as 1 atmosphere, which makes sense. Okay? So the further you get from sea level, the lower your pressure gets. Lower you get, so going down into the ocean, the higher your pressure gets. Okay? Why is this important? It's important for a lot of reasons. One important one that you probably saw this morning is weather. So the temperature that you see in a lot of ways depends on the pressure systems that are moving through. Atmospheric pressure is also important if you ever drink out of a straw. So how does a straw work? Are you just sucking the water up through your straw? No, that's not a thing. So what you're doing is you're changing the pressure inside of the straw by sucking on it, and then the atmospheric pressure around you pushes the water up into the straw. Huh? Now you can think about that every time you drink out of a cup. And so if you have a really tight seal, like in some of these more intense Camelback type water bottles, it's harder to drink from them because they're closed really tight. So if you're having a hard time drinking out of those like I do, I don't know why, you can break the seal a little bit by opening it, and that allows more pressure, not more pressure, but the pressure to really be equal to atmospheric pressure and come up, push the water into your straw. So there you go. That's why pressure is important to you. Also, do you like breathing? That's because atmospheric pressure stays relatively constant. So there you go. Okay, so what are the different units? We have a bunch of different units for pressure, and you have all of them on your equation sheet. So right here, don't worry, you don't have to memorize these. I give all of the conversions to you, so don't ask me about memorizing them. The answer is no. Here they are. Okay, but let's talk about them some. So we have a bunch of different units that we use for different reasons a lot of the time, but the conversion usually is to 1 atmosphere or 2 units of atmospheres because we have an important constant we're going to talk about soon. Another common one that's used is millimeters of mercury. So 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 760 torr. And if you're thinking about sig figs, all of these can be considered exact values, so don't worry about sig figs with these. Okay, this is equal to 1.01325 times 10 to the 5th pascals, or 325 kilopascals, or 14.7 psi. So you can convert between any of these units of pressure using these conversion factors. So we use millimeters of mercury for a lot of time reporting weather. Also, bars are used a lot of the time. Pascals are used a lot more for physics. PSI is used for more practical things like tire pressure. So there's a lot of different applications for these different units. All right, so we're still on pressure because there's a lot of things to think about. So how do we measure pressure? Basically, it's a lot like how a straw is used. It's an instrument called a barometer, and it was developed by Marco Torricelli, which you'll see is where some of our units come from for measuring pressure. Basically, in science, if you invent something, they're going to name it after you. So that's kind of one reason to get excited about that. So that's why 1 torr is equal to 1 millimeter of mercury. So what did he figure out? Basically, if you take a container of mercury and you put a tube in it that has a vacuum, the air pressure will push the mercury up the tube. And the height of the mercury in the tube tells you the atmospheric pressure. Okay? So you can measure it in millimeters of mercury, because that's what's in the barometer. Okay? So you have mercury, or Hg, forced into a tube by atmospheric pressure on the surface of the mercury. Why do we use mercury? Seems like a pretty toxic thing to be using in a measuring device. The answer is yes, that's true. But if you use something like water, which is a lot less dense than mercury, the tube that you would need to measure the same amount of pressure would be about 30 meters tall. So too tall to be practical in a lab. 30 meters is like, up to the ceiling or more. So the reason why we used mercury is because its density is about 13 grams per centimeter cubed, which is about 13.6 times higher than water. So because it's so dense, it requires a much smaller column. So kind of dangerous, but smart. We don't really use mercury for anything anymore. We have other measuring devices, but that's where it comes from. So that's where units of millimeters of mercury and torr come from, and that's why they're used interchangeably. Okay? The other thing you can use is if you have a closed system and you're measuring the pressure of a gas in a reaction, excuse me, you can use a manometer. So the point of this is to measure pressure in an enclosed container. So if the pressure of your gas in your container is greater than atmospheric pressure, then what you do is you look at the column here, and you would say that the pressure of your gas is equal to atmospheric pressure plus the pressure of the mercury. So this is probably really hard to read in this graphic, but if atmospheric pressure is 750 millimeters of mercury that you would read on a barometer, and the pressure of the gas is this height right here, which is 45 millimeters of mercury, then you just add them together. So the total pressure of the mercury. Pressure of the gas would be the sum, so 795 millimeters of mercury. Okay, so the pressure of the gas exerts a force on the mercury and pushes it out of the tube. So this height of the mercury is 45 millimeters of mercury. So it gets added. Okay, if the pressure of the gas is less than atmospheric pressure, then the gas can't push the mercury up the tube. It stays on this side of the tube. So then the pressure of the gas is atmospheric pressure minus the pressure of the mercury. So again, we start with 750 as your atmospheric pressure. You just get that from measuring it on a barometer. The pressure of your mercury in this little guy is 24 millimeters. So then you subtract. In this one we added. So the pressure of our gas is 726 millimeters of mercury. Okay, so you can visually understand if it's making more pressure than atmospheric pressure, it's going to push the mercury out. If it has less pressure, then the mercury stays on the left side. Okay? In general, gases move from areas of high pressure to low pressure, and this is what leads to atmospheric or weather conditions. Okay? So if you have a larger pressure difference, you're going to have stronger gas flow. If you have stronger gas flow, what do you notice in real life? So if we're sitting in a low pressure system and in quickly comes a high pressure system, what would you notice? Wind, yes, or extreme weather. Yeah, so that's because of how gases interact in the atmosphere. All right, cool. Good stuff. Okay, so now let's talk about how all our different variables work together to make simple gas laws. Okay. Sorry for all my awkward coughing and throat clearing. Finally got antibiotics for my sinus infection, so I'm about to feel so much better. Love antibiotics. Okay. I love modern medicine. Okay, so Boyle's law, it brings me back to kind of the beginning of the semester when we were talking about dose and units and all of that, and how, you know, you come to the doctor and you're sick and they have to know your weight and everything to correctly prescribe you enough medicine to feel better. Just so much good science that goes in there. Okay, anyway, let's talk about the gas laws. So there are 3 simple gas laws, and everything is going to relate to volume. So how each unit directly is related to the volume of your gas. Okay? So these are relating our units to volume. And so this is basically experiment 10, where you're figuring out the gas laws or confirming the gas laws experimentally. But I'm going to tell you what they are right now. All right, so the first gas law is Boyle's law. A guy named Boyle figured it out, so it's his law. Okay, so what this says is that at constant temperature and number of moles, the volume is directly proportional to the inverse of pressure. Okay, so we can write a simple gas law, which is P1 V1 equals P2 V2. Kind of looks like a dilution equation. But basically this is saying that as you raise the pressure, the volume goes down. Okay? So if you double the pressure, then volume is halved, and vice versa. And you can figure out exactly what it is by using this equation. Just want to make sure that your units match. So I can show you a quick little demonstration of this. Boyle's law. Okay, so here we go. With Boyle's law, what we're going to do is, in this demonstration, they're applying a vacuum to this chamber. And so they're decreasing the pressure by pulling gas out of the chamber, and so the balloon is expanding. Once the pressure gets back to normal, so you turn off the vacuum, now the balloon goes back down. So the pressure goes up, the volume goes down. He also does this with some marshmallows. It's pretty cute. Okay, so he's going to put a marshmallow peep in there. He's going to turn on the vacuum, so take away a bunch of the pressure. We'll see what happens to this little guy. Oh my gosh. Mega peep. And then it goes back down. Shrinky peep. And actually, when you take some of the gas out of the little marshmallows, it kind of doesn't go back to its original shape because it pulls the gas out of the structure itself. This is shaving cream. So shaving cream is a foam, which means it has gas dissolved inside of the material. And so this effect is really dramatic because all of the gas starts expanding. And then I don't remember if he shows the release of the pressure. Yeah, no. Okay, so anyway, I just think that's a nice visual for what happens when you change one of those variables. Okay. The next law we're going to talk about is Charles' law. So Charles' law says you're keeping the pressure the same and the moles the same. So what variable are you changing? Yes, temperature. So the volume is directly proportional to the temperature. So we can write V1 over T1 is V2 over T2. So this one was an inverse relationship. This is a direct relationship. But the thing about this is it's only direct if your temperature has units of Kelvin. So if the temperature is in Celsius, there's not a linear relationship. So you can still say that as the temperature goes up, the volume goes up, But if you're talking about Celsius temperature, then it's not linear. So when the temperature doubles, then the volume doubles. If temperature is halved, then the volume is halved, etc. So they change in a direct proportion. So this picture is kind of hard to see. I'll show you the real-life version of this. Okay, so in this demonstration, what they're doing is they're taking a balloon and they're pouring liquid nitrogen on it. Liquid nitrogen has a temperature of 178 Kelvin. There's no negatives in Kelvin. So it's very cold, is what I'm saying to you. So what happens to the balloon when you make it really cold? It's going to shrink up a bunch. Oh, my goodness, the volume is so small. I don't know what this ad is. Okay, as it comes back to normal temperature, it starts to expand. Yes, so as the temperature increases, with the liquid nitrogen kind of evaporating off, the volume goes back to normal. It's kind of like, have you ever bought balloons on a cold day and you buy them and you're so excited to take them to your car and you're like, what is this deflated nonsense? I just paid good money for this. But then you put it in your car and you warm it up and you're like, oh, it's actually fine. It's the same. Oh, we should better watch this one too. I haven't seen it, but it seems like it's going to be really good. Frostbite Theater. They probably cool a bunch of stuff. Put it in there. Stop talking about it. Just do it. Koosh ball in the water. Do you guys remember koosh balls? That was really a long time ago. That was back when I was a kid. All right, it's just dying. And pieces are breaking off because it's all brittle now. It wasn't as exciting as I thought. Oh, whoa. Now it's really starting to get wonky. It's losing some pressure in there. Yeah, okay. Apparently it self-destructed at some point where I fast forward. We better get back to that. Where does it explode? Oh! All right. So it explodes. Anyway, putting stuff in liquid nitrogen is super fun. So if you want to do that, we do some demos for students. You can work with us. Yeah?
Okay, so would that be the same thing, like you reverse put it in hot water, you put it in hot water?
Yeah. It kind of collapses.
No, like if it's denser,
Yeah, okay, so yeah, if it's hot, then it should expand. Yeah, exactly. That was fun. Okay. I feel like I was saying something at some point, not about koosh balls. Anyway, you get the point. So, as the temperature goes up, the volume goes up. As you cool it, the volume also goes down. All right, so the last one is Avogadro's law. Avogadro was all about the moles. So this one relates volume with number of moles. So we can write V1 over N1 is V2 over N2. So if you double the number of moles, then your volume will double, which makes sense, right? If you put more gas in a balloon, it should expand because you have more of that gas. So this one's fairly intuitive. Okay? And again, vice versa. So it's not super useful to only think about these individual laws all the time. It would be more helpful if we could put them all together and have a mega law, or perhaps an ideal law. Yes, you've probably seen this before. So if we take all three of our gas laws that allow us to relate each of the variables to volume, right? So we said that volume is directly proportional to inverse pressure, and volume is directly proportional to moles, and volume is directly proportional to the temperature in Kelvin. Let's put it all together and say that volume is directly proportional to moles times temperature divided by pressure. And instead of proportioning stuff, let's give it a constant so we can write an equation. So the equation is volume equals a constant times NT over P. Or, the more commonly found version of this is PV equals nRT. Or PubNert. Easier. So basically in Chapter 5, we're going to PubNert all day, every day. Okay? What even is R? You probably should know what that is so that you can apply this equation, right? So this constant is 0.08206 liters times atmospheres over mole Kelvin. Do I give you this constant? Yes, it's right here. But you have to know that you need to use this version and not this version, which we'll use later. So what's awesome about this constant is it basically holds all of the answers within it. It's like a magic factor. Okay? So it tells you all of the units you need to know. You need volume in liters. You need pressure in atmospheres. You need moles in moles. That's self-explanatory. And you need temperature in Kelvin. But I'm going to highlight that, the temperature in Kelvin, because everybody always forgets. And then it's like, why didn't I get the right answer? It's such an easy equation. Yes, it is, if you put all your units in correctly. So if you have this awesome equation, PubNert, and you know 3 of your 4 variables, you can find the 4th just by doing unit canceling, which we've been doing all semester. See how it all just beautifully comes together? I love it. Okay, so let's do an example because everything makes more sense when you look at an example. So let's say we have 0.552 moles of gas, and that occupies 8.5 liters at 305 Kelvin. So what is the pressure of the gas? So we always write PubNert. The tricky thing about PubNert is you have to be good at rearranging your equation to solve for the variable you want. Okay, so P equals nRT over V. Although I have to add the caveat that it actually doesn't matter if you know how to rearrange it. If you just plug in all your things, solve for your unknown. Maybe it helps you to rearrange it once numbers are in there. I don't know. But I like to rearrange it, so P equals nRT over V. So we're just going to plug in everything into this equation. So N is the number of moles, 0.552 moles. R is this awesome number that has all of our units in there, 0.08206 liters times atmospheres over mole Kelvin. And you'll probably say, do I have to write that out every time? And my answer is obviously, because it helps you cancel all your units and know what unit you should give me at the end. Because if you report a unitless value, what do? Yeah, I mark it wrong, at least partially, so might as well not get it wrong. Okay, and the temperature is 305 Kelvin. And we're going to divide that by the volume, 8.50 liters. Notice how all of these numbers were already with the correct units, and I'll show you how we cancel them out. So, moles, up here cancels moles in the denominator of our conversion factor. Then Kelvin gets canceled with the temperature, Kelvin. Then liters, cancel liters, and you're left with the unit you needed all along, which was atmospheres. Boom, nailed it. So your answer is 1.63 atmospheres. So writing it out is a little bit tedious, but I find it really helpful to know, A, whether you rearranged correctly to make sure everything's canceling, and B, what your units are for what you're looking for. Stop yawning so much. It's only Monday. How dare you? Okay. So, all right. So R is awesome because it's a constant. So a lot of the times what we're solving for with these gas law problems involves initial and final states. So what does that mean? It means you have a gas in a container with some conditions. Like 5 of you yawned after I said that. That was hilarious. So I think an involuntary thing. I actually got yelled at once for yawning in class too. Apparently I did it very loudly, and this normally really mild-mannered man who does Iron Man's and like nothing frazzles him, was like turned around and was like, "If you're so tired, get out of my classroom." And I was like, who's he even talking to? Then he was pointing at me and I was like, oh God, I irritated the most quiet man on record. So I'm very like, aware of yawning since then. It was traumatic. Okay, I won't call you out individually, so that's one thing you cannot worry about. Okay, anyway, back to this. So these initial and final states are what happens when you take your gas in your container and you change something about it. So you want to know what's changing, okay? So we have Puvner. We know that R is constant. So even if you change all of your other variables, you can set two equations equal to each other and solve for R. So if you rearrange this for R, we know R is equal to PV over NT. So the pressure initially times the volume initially over the initial moles and the initial temperature is equal to those same variables at the new conditions. So if you do something to your gas, you can figure out what's happening after you've changed it using this equation. Okay? So let's do an example. Suppose a gas in a closed container has a temperature of 290 Kelvin and a pressure of 1.38 atmospheres. What is the pressure when the temperature is raised to 400 Kelvin? So we have this initial and final thing, but some things are constant. So let's think about the things that aren't changing so we can simplify this set of equations. Okay? So what thing is not changing if you have a closed cylinder? Volume, exactly. Yes, the volume is constant. So we know that V1 equals V2. Is anything else not changing? Moles, yeah, because the gas can't leave or enter your closed cylinder. So the moles are constant, which means that N1 equals N2, which also means that if we start with P1V1 over N1T1 equals P2V2 over N2T2, then the volumes are going to cancel because they're the same, and the moles are going to cancel because they're the same. So what's nice is we don't have to write a separate gas law relating pressure and temperature. We can just use this before and after and think about what stays the same and what changes to write a new law, which essentially says that P1 over T1 is P2 over T2. And again, notice how the temperatures are in Kelvin, not Celsius. So let's just plug in our values. So the pressure initially was 1.38 atmospheres, and the temperature was 290 Kelvin. Now we don't know the pressure, and the new temperature is 400 Kelvin. So you cross multiply and divide, and you get that P2 equals 1.90 atmospheres. Okay, so as the temperature went up, the pressure went up. Okay? All right. So, a lot of the time, maybe let's hydrate quick, then we'll finish strong. Finally got my hydrate or dihydrate sticker. I'm ready. Classic. Okay. So, a lot of the time reactions are done at what we call standard conditions because it's easier to calculate stuff for them. When we're talking about standard conditions for gases, we talk about STP. So standard temperature and pressure. That's what STP is. Standard temperature and pressure. What is the standard temperature and pressure? So the standard temperature is 0 degrees Celsius, so 273.15 Kelvin. And the standard pressure is 1 atmosphere. Do you need to know what these are? Yes. You need to know, because I will say something's done at standard temperature and pressure, and you'll need to know that these two things are true. The temperature is 0 degrees C, the pressure is 1 atmosphere. Okay? So what's true at STP? At STP, a mole of gas has the following volume. So the volume at STP is equal to nRT over P. So let's figure out what the volume is at these conditions. So the number of moles is 1 mole, R, 0.08206 liters times atmospheres over mole Kelvin. The temperature is 273.15 Kelvin. Notice we're using the Kelvin temperature, and we're dividing by the pressure, so 1 atmosphere. So under STP conditions, a mole of gas occupies 22.4 liters. So this is true for 1 mole of any gas. If you want to remember this, you can, but you can literally calculate it whenever you want. But if you know it, it's a useful conversion factor sometimes. Okay? So because this is true for 1 mole of any gas, we say that gas is immaterial, which means even if you have the same, even if you have different mass, you can have the same volume. Okay? So let's do an example. Determine the mass of chlorine gas in a 10-liter container at STP. So, if we want to know the mass of the gas, what do we have to know first? Can we find grams from our Puvnert equations? Not directly. First, we have to find moles. Exactly right. So the number of moles is equal to our volume times this conversion factor that we just figured out. So we know that 1 mole equals 22.4 liters. So this gives us 0.446 moles of Cl2. Then we can take our moles of Cl2, and convert to grams using the molar mass of chlorine gas. Remember this thing? We haven't done this in a while. So this is 31.6 grams of Cl2. If it's annoying to you to have to think about this conversion factor in addition to the many others you've used so far, then don't worry about it. Or just use Puvnert. And solve for n using the conditions at STP. So n is equal to PV over RT. So the pressure at STP is 1 atmosphere. The volume given in the problem is 10 liters. R doesn't change, 0.08206 liters times atmospheres over mole Kelvin. And the temperature at standard temperature and pressure is 273.15. So when you solve this, you still get 0.446 moles of Cl2, and then you just multiply by the molar mass to get grams. So you get still 31.6 grams of Cl2. So that's not any different. It's just whether or not you know that conversion factor. So you see, the tricky thing in Chapter 5 is really not do you use Puvnert, it's how do you use it.